All right. Good afternoon, everybody. Happy Tuesday. Hope you guys had a nice Thanksgiving weekend. So basically, this is our last week of the semester. So what's going to happen for this week? I'm going to finish up a few more things with Bellman-Ford dynamic programming algorithm. Um, and what's sort of the plan? I don't have a study guide just yet, but I'll have a study guide up for sure by our Thursday's class. So on Thursday, I'll go over the study guide and go over solutions on the past homework assignments. I won't be able to go over the solution on newest one because it's still not really, it's still due, or it's still in the process of being done by us, but I'll have the solutions posted on that once it's submitted. But I'm going to go over, if I finish early today, I'll go over some of the assignment results up to this point to give you an idea, because the exam will mostly cover content from the homework similar to the midterm. So I may have a few conceptual questions on the exam. And then, of course, there's several questions like from homework, just different, different problem, but same, different input or different graph or whatnot, but same problem, basically, same algorithm. So it's nothing too fancy there. So it should be a relatively good final exam result. I'm hoping for, just like the midterm was overall pretty okay. Um, Also, I have to get the ABET quiz ready for this class. So, the ABET quiz is that one quiz you take, which is end of the semester. It's sort of a departmental quiz that is just designed as mostly for us to kind of it's for accreditation purposes mostly. So that'll be an online quiz I'll have up hopefully soon. That'll be due most likely around Sunday of this week. It'll be due by. And I guess the incentive is I'll give extra credit points for the final exam, just for completing that quiz. But of course, do your best on it. Don't just, even though I'm not going to really grade it, and I mean, it's going to get graded for statistical purposes, but it won't really count towards your grade, how good or bad you do on it. But try to do your best, of course, on it. As always, don't just purposely do bad. And yeah, of course, I'll give extra credit points for taking that ABET quiz. So shouldn't be. So I'll have that quiz up hopefully sometime by midweek, and it won't be very. It'll be a 15-minute quiz or so. It shouldn't take long to do it really. Multiple choice all the way through. So that's basically what's sort of what's in store for this week. Next week will be our final exam, and I'm not sure if it's on Tuesday or Thursday. It'll be from 1 to 3. I just don't know if it's a Tuesday or Thursday class. I have to double check the final exam schedule, because it's always interesting how they schedule all that. But I know it's either Tuesday or Thursday of next week from 1 to 3 is the idea. So that's Tuesday. Okay, I'll double check the exam date. And yeah, so for ABET quiz, just complete the quiz, and if you complete it, you get credit points for a final. But do your best, of course. But there's no, as long as you do it, extra credit points will be given for your final exam. So um, no pressure there. But of course, try to do your best, of course, on the ABET quiz. Um, but I'll double check it myself to make sure it is. But anyway, either way, it's from 1 to 3, so it should be enough time to work on it. It won't be comprehensive. So the exam is going to cover content after the midterm. So I believe it sort of starts with that 2-3 tree content. Yeah, so 2-3 trees is when it's going to begin. So from that point on, so the best way to study for the exam is go through your old homework assignments. I'm going to go over, the solutions of them either a little bit today or for sure on Thursday, and just go through all those homework, because that's going to be a good starting point to prepare for the final exam. So anyway, I guess now I'm going to just go back into our notes from last time, which was a while ago, which before Thanksgiving. So let me go ahead and just start a screen share. And I believe we were covering Bellman-Ford's shortest path algorithm, or minimum weight algorithm. Okay, so I'm also going to go over maybe the assignment 7 that covers Bellman-Ford as well, since I didn't really cover it in so much detail just yet. But anyway, this is a pretty simple algorithm. So all we're doing is just this loop right here. So we're going to have this for each loop, and all we're doing literally is just picking an edge, and we're going to try to relax it by updating the weighted path to the node. That's all we're doing basically. That's it. And we're doing this many times until either And the worst case you have to do is v minus 1 number of times. But really, once we don't relax in one pass, then we're done. So I'll do several different examples of this on our graph right here. So I'm going to maybe start over again just to kind of recap this if in case, you can watch the video, of course. I'll recap it. So I'll start over again just, not in a hurry or anything. So why not? It won't even take very long to even do this example, so it's not really a big issue. So I'm going to go ahead and just copy this. I don't have to redraw every single time. Let's assume we start from the beginning again. So initially, everything will be infinity in our weighted array, because right now we don't have a path. So it's also a single source shortest path, which means we're going to find the minimal weight path from S to every node in the graph. So basically that means S, we're going to set this to 0 because S will be our start node. So whatever is our start node, we're going to assign 0 to that weight. And we're going to go ahead and go through edges, and the green numbers are going to denote the weights of the edges, and red numbers will be the order in which we're going to process them. Now, any order can work, but I'm going to choose this order just because. So right now, the first edge I'm going to choose will be A goes to B. It's the first one, because that's the order I'm going to pick, just because. So right now, we see here that a weight of A is going to be, well, it's right now infinity. That's the weight of A. So infinity plus the edge weight from A to B is 5. So B's weight will still be infinity. We can't update B really. Okay, fine. Now our next edge in our sequence, I'm going to go ahead and just sort of mark this. So we first looked at this edge. The next one's going to be, well, B goes to A, because I labeled these numbers, which will tell us the order in which we're going to process edges. Okay, so we have B goes to A. So B has the weight of infinity, because in our array, B is infinity, plus -2 will still be infinity, so we can't update the path, the edge that goes from B to A. We can't update A because, well, it's not really better. Okay, fine. So we're done with this edge next. The next step in our for each loop, our third edge will be D goes to B. So D currently has the weight of infinity. So infinity plus 7 will be still infinity, so B can't be updated at all. So B will remain still at infinity. The next edge we have is looks like number 4, so from C to B. Okay, so from C to B, well, we first look at the weight of C, which is going to be infinity. And it goes to B with the weight of -3, which will still be infinity. Infinity plus -3 is infinity, so nothing updates there. So that's kind of a bummer, but that's how it is, though. The next step, step 5, we're going to try to look at this next edge, which will be A goes to D. So A has the weight of infinity, plus the edge weight to D, which is -4, which is still going to be infinity plus -4 is infinity, so nothing happens there. So we're done with this edge. Then step 6. Okay, so now at step 6. Okay, we're looking at this edge from S goes to C. So S has the weight 0. And then, so S0 plus the edge weight to C is going to be 7. So we're able to relax C. So C now is going to be 7. So I'll put red here, which red means we relax this, node. So basically, we found a better weight from S to C with the weight of 7, because S has the weight 0, which is right here in this array, plus the edge weight is 7, which is less than infinity, so we updated C. Something updated, at least, finally. Then step 7, we're going to look at our next edge, which will be from D goes to S, and D has weight infinity, plus 2 is infinity, so nothing happens there. Then we have step 8, S goes to A. So S has the weight of 0, because looking at our weighted array, S is 0, plus the edge weight 6 to A will be 6, which is going to be an update. So we're going to reweight A to be 6. So we relaxed this node. Now we're done with that step. Step 9, we're going to update C goes to D. And because we updated C earlier, we actually can update D right now. So let's say, for example, if I would have actually processed C to D first and then S to C next, then that wait for D could not be updated right now. It have to be next pass. You'd have to update this. So the order in which we update the order we look at the edges determines sort of how fast we can compute our shortest path. Either way, though, after v minus 1 steps, it will get our result. But we can see here that if I would have looked at CD first and then SC afterwards, then C goes to D. That weighted path to D would not be updated just yet. But because I did C S to C first, I can update C to D. So now we see here that our step 9 will be C goes to D. C has the current weight of 7, plus the edge weight from C to D, which will be 9. So D can be updated to 16. Then our last step, step 10, well, we're going to have A goes to C. So right now we're going to basically have, okay, so A has a weight of 6, plus 8 is 14. So C would be 14, but we already have a better weight that has a weight of 7, so we don't do anything there. So after our first pass, we're able to reweight A, C, and D. Now in the worst case, however, we really would only be able to update A and C. Because suppose that we try to look at every edge first, and then at the very end we look at S to A, S to C. Then what would happen is D would not have been updatable actually in the first pass. So suppose if I would have tried, let's say C to D, I would look at that edge before I look at S to C, then you can notice that D would not have a current weight. It would be infinity still. So the order does make a difference, but it's going to still work. It's just going to take more steps if we have a bad sort of ordering. But anyway, this is going to be our current scenario. So for our second pass, I'm going to copy everything over from our last pass. And we're going to keep on trying this. We're going to try again. The same process. We're going to go ahead and go through every edge in this order and try to weight, try to weight all of the nodes, basically, until we can't find a better one. This is going to be a little risky. Okay, it wasn't too bad. A little risky, but not too bad. This one, okay, and this one comes next. Good and good. Okay. So we do the same exact thing all over again, but now we have new elements. So previously they're all infinity, but now we have these values. So using these old values, we can go ahead and reweight possibly new elements. Let's try this again. So for step 2, we're going to process the edges in the same order as before. So first step, we're going to look at A goes to B. Okay, so right now, A has the weight of 6. I'll zoom out a bit so you can see the graph and this array. So A has the weight of 6, and then has the edge weight from A to B, which is 5. So 6 plus 5 is 11, and B, I can reweight this now to be 11. So I found a better pathway than before. So now we're done with this edge. So step 2, we're going to now look at our next edge. So we have B goes to A. So B now has a new weight of 11 plus this -2. So B, which is 11 plus -2, 9. It's not a better weight to A, so we're not going to relax this node. Okay. So now step 3. So step 3 is going to be the edge that goes from D going to B. So we have D with the weight of 16 plus the edge weight of 7 to B, which is going to be 23, and it's not better than our current sort of path weight, so we're not going to relax. We can't really modify that. Oh well. Step 4. Our next step is going to be the path from C goes to B, that edge. So C has the weight of 7 plus -3 is going to be 4, which is less than B's current weight of 11. So we're going to update this from 11 to, I guess, to 4. It was 11 in this step, but now it's going to be 4 because from C, we found a better path to B. And luckily, because now we have a new weight for C, we're able to update all of C's neighbors. So that's going to be step 4. The next step, step 5, we're going to have A goes to D. Okay, so A currently has the weight of 6 plus that edge weight from A to D, which is -4, it's going to be 2, which is better than D's current weight of 16. So we're going to update this from 16 to be 2. So from the previous step, we got 16, but now we have a better weight, which is going to be 2. Because we have A's weight of 6 in this step, and the 6 for A's weight 6 plus -4 to D is better than 16 that we had in the last step. Step 6 in our for each loop, while we look at this, we have S goes to C, and that's not going to update anything because S has the weight of 0 plus 6, so okay, well, nothing updates there. Step 7, D has the weight of 7 actually right now at the moment, plus the edge weight D to S, which is going to be 2, which will be 9, which is not better than S's current weight, so we can't update that. Step 8, well, we're going to look at, I guess, S goes to A. Nothing updates there either because we already did that earlier because S has a weight of 0 plus 6. Nothing updates there, so oh well. Step 9, C has the weight of 7. Step 9 will be that CD edge. C has a weight of 7 plus 9, which will be 16. Is not better than D's current weight, so oh well. Step 10, A has the so we take this edge, A goes to C. A has the weight of 6 plus the edge weight from A to C, which will be 8, which is 14, is not better. So we're not going to update that either. So this is going to be our current weighted array after our second pass. So we currently have the shortest path from S to A will be 6. Shortest weight path from S to B is 4. Then for C it's 7 and D is 2. But notice we have some red marks, which means that we were able to update something. So we're not done. We have to keep on running this again because we updated B and D. Because of that, maybe there's going to be better paths from B to a different edge, or B to a different neighbor. So because of B's update, maybe there's going to be a better, we can find a better sort of weight potentially. So let's go ahead and work this one out. So I'm going to go ahead and copy this because we're not done. We still have more work to do. So in our third pass, I'm going to copy everything from our last pass. We have 0, 6, 4, 7, 2. And we're going to try to hopefully update some of these. So I'm going to go ahead and erase these marks, and we're going to start all over again. It's a very tedious algorithm, but it is not really too hard to follow, actually. It's just very tedious. But then again, every dynamic programming problem is kind of tedious in a sense, so it's not really, it's not a shock that it is a little tedious. Okay, so now we're going to start all over again on this third pass. Okay, so I'm going to go ahead and zoom out so I can see the array and the image. Okay, so now, again, step 1. So we're going to first look at the edge A goes to B. So A has the weight of 6, plus the edge weight to B is 5, so we can't update B because this would be a bigger value than B's current. B is 4, so we won't do anything there. Then step 2, in that for each loop, we look at our next edge. So B goes to A. So B has the weight of 4 plus the edge weight from B to A, which will be -2. So we found a better path to A through B. So A is now going to be 2. I just found a better one. So in the previous step, we had 6, but now we found a better one because from B with the weight of 4 plus -2 is going to be 2, which is better than the last one we had for A, which was 6. So because it took us so long to update B's weight, we were finally able to update A to a shorter path because we finally got we got our our good sort of pathway to B, finally. So anyway, we have that. Now step 3, our next edge, so D goes to B, and D has a weight of 2 plus 7. That's not going to be a better weight to B, so forget that. Step 4, we have the edge from C goes to B, so C has the weight of 7 currently. And then going to B, well, plus negative 3 is going to be 4, so we can't really update B, so we're done with that. Step 5, look at A goes to D. So A has the weight of 2, because we just updated it recently to the weight of 2. So then at 2 plus that edge weight to D, negative 4, is going to give us a better weight. So D now is going to be negative 4 from now on. Look at this, A goes to D, so A has the weight of 2, plus the edge weight from A to D is negative 4, so D now is going to be negative 2. We're able to also reweight that as well. So step 6, our next edge, so S goes to C. That's not going to update anything. We already know that because C is going to be 7. It's not going to make any difference at all. Step 7, so D goes to S. Well, I guess D has a weight of negative 2 plus 2, which will be 0, which S's weight is still 0, so nothing updates there either. Step 8, S goes to A, so A has a weight of 2. S going to A with weight of 6 is not going to make any improvements, so nothing happens there either. Step 9, so C goes to D. So C has a weight of 7 plus the edge weight of 9 is not going to be better for D, so nothing updates there either. And then our last one's A goes to C. So A has the weight of 8 plus, sorry, A has a weight of 2, I'm sorry, plus the edge weight from A to C, which is 8. So 8 plus 2 is 10, which is not better, so we can't update that either. So after the third pass, we notice, well, we're able to update some stuff. So because we updated A and D, that means that there's still better paths that go from A to a different node. Because updating A could result in getting better paths from A to all of its neighbors. And same thing for D, which means that, well, we have to keep on working because we can't stop yet because we can't guarantee that maybe from A to D there could be better paths that could arise. So we have to keep working. So our fourth pass, I'm going to go ahead and copy everything from our last pass. Okay. So in our fourth pass, let's go ahead and erase all these marks, and let's go ahead and run this again. So hopefully nothing updates anymore, because this is kind of getting a little too tedious now for me. So hopefully no more updates happen. I have a feeling there won't be any more updates, though. That's my guess. But, one way to find out, though. So I'm going to now look at everything in our graph. So again, same process. We're going to go through step 1, step 2, and so forth. So step 1, look at this edge. A goes to B. A has the weight. I'm going to go ahead and just sort of move this out. So A has the weight of 2. Looking at this, we have the weight of 2 for A. Plus 5 is not going to be a better weight to B, so nothing we can do there. The next edge, B goes to A. That's the next step in our for each loop. B has the weight of 4. Plus the edge weight of negative 2 to A, which will be 2, which is not an improvement, so nothing happens there. Step 3, so now here's the issue. So we updated D earlier. Let's see if this leads to any updates now. So D has the weight of negative 2, plus the edge weight to B, which is going to be 7, which is 5, so it's not a better path to B, so well, I guess that's rejected. We didn't get a better path. Step 4, looking at C. So in the last step, C didn't update, so really this is not going to cause any change, I don't think, but let's just look at this anyway. So C has a weight, so looking at the edge, C goes to B in step 4. This has the weight of 7 plus negative 3, so B will have the weight. It's not going to update B's weight, so we can toss that. Step 5, A has the weight, so we're going from A goes to D. A has the weight of 2 plus negative 2, which is negative 4, sorry. So D's weight is not going to update because the weight is still going to be, because taking A's weight of 2 plus -4 is -2, and D already has -2, so nothing updates there. Step 6, well, that won't update because we already, let's see, has the weight of 7. We can't do anything there. Step 7, D goes to S. Well, since D has the weight -2 plus that -2, nothing happens there. S will still be 0 for its weight. Step 8, A has the weight of 6, or of 2, sorry. So S going to A, S with the weight of 0 plus 6, won't update A's weight, so nothing we can do there either. Step 9, C has the weight of 7 plus edge weight 9 to D. Is not going to be a better weight, so throw that out. Then step 10, A has the weight, so we're going from A to C. A has the weight of 2 in our weighted array, plus that edge weight 8, which will be 10, which is not better. So we notice over here, nothing updated. That means we're done. So we have five nodes in our graph. So really, this will take exactly, in the worst case, v minus 1 steps. So we ran actually 4 steps. So we did it in the worst possible case. Now, there's a chance that depending on what order you actually work these out, in one pass, you can get all your smallest weight already, and in the second pass, nothing would update and you'd be done. So because I chose this ordering of how we're going to process edges, I ended up taking 4 passes to finally, well, actually 3 passes to get my best weight, but on the 4th pass, though, I was able to conclude that nothing updated, so that means nothing ever will update, so I'm done. But there's a chance that depending on what order we actually process this. So for example, what if I would look at S goes to A first, S goes to D, S goes to C second, like that, and then I could have updated. So in the first step in this example, I didn't update B, and I actually didn't get D's best path right away. So what could have happened is I could have a different order in which I could have processed my edges. Where in fact, what could happen, like let's say, for example, let's look at this graph just really quickly. I don't want to try to mess with this example right here, but let's say we have this graph. Just something like that, for example. So I'm going to have maybe S, A, B, C, and D. And I'll have maybe, let's say I'll have like 1, -2, 1. This will be 1. This will be, I guess, 3 and 2, like this. So what could happen is I could, my first pass, what if I have my order in this? Let's say if I first do this, then this, then this, then I'll look at this edge next, then that edge, and then this edge. What if I do in this order? Then in my first pass, actually, I would already have my shortest path already solved. So my first pass, I get my answer. My second pass would just kind of validate that nothing would update, because really we stop this once we have no updates anymore, we can stop. So in our first pass, you would get our best paths, but we can't be sure it's our best just yet. We have to do one more extra pass, and if nothing updates in our second pass, then we know we're done. We can stop. We don't have to run this loop of v minus 1 number of times. So over here, this for each loop will run no matter what, but the outer loop doesn't have to run v minus 1 number of times. In the worst case, it will, but it could sort of exit early. If no updates happen in one iteration of this for each loop, that means we can stop right away. But it depends on the order in which we process edges. So in the example I did right here, this is probably not the best order we chose, but it'll still work. It'll take more passes. But you have to at least have to do 2 passes no matter what, because the first pass, in the best case, would compute all the best weighted paths, and step 2, or second pass, would just kind of validate that, okay, nothing updates anymore, which means, okay, we can stop. Because really, for this algorithm, we're taking the path weights from the previous step, and we're going to try to update all of its neighbors. So for example, in our second pass of our left graph, we updated B and D. So because of updating B and D, we were able to update other elements because B had a better path. So maybe from B, we actually found a better path to A actually, because look, we have a weight of 4 for B, and using that new weight 4, we find a better weight to A. So if you update something in our graph, there's a chance that it could lead to more updates later on. If nothing updates in one pass, then we could keep on running. So for example, let's say after 2 passes, we have our nothing updates. We could do is v minus 1 number of times still, but nothing would happen. It's redundant. We're doing the same thing again, expecting a different result. So nothing's happening at that point. Nothing will update. So we're wasting our time by doing that. But that's the idea for Bellman-Ford algorithm. So for the homework, you have to pretty much do exactly this. So there was a question on the homework as to I guess there was some issue where somebody had a question on the order was kind of weird and how do we process that? So I guess I can discuss that right now as well, since we are kind of on that sort of topic. So I'm going to go over, pull up this PDF for a second to give you an idea. So it's kind of a bizarre algorithm, but it's actually kind of an easy one at the same time. It's just kind of strange. It's not really as intuitive. So that was a bright light that flashed right there. So okay. I can just go ahead and copy and paste this into OneNote. I probably can't. So, okay, I'll have to like just work it out like this. So what will happen is, since we have this order, I'm gonna go ahead and just kind of process it. So you have B goes to A first. So I'm gonna put a 1 over there. A goes to B, I'll put 2 over there. D goes to B, that'll be a 3. C goes to A, that'll be 4. C goes to D, that'll be 5. Then we have, let's see, 1, 2, 3, 4, 5. A goes to capital C. That's a typo right there, but not a big issue though. So A goes to C, that's going to be step 6. And S goes to A, that'll be step 7. And then S goes to C will be step 8. Okay, so it's actually not a very good order in how we're going to do this, but I'm doing it on purpose to kind of force you to sort of do more work, I guess. So in this situation, I just go ahead and just create this array. So I'm going to have maybe my W array below. I'll try to use a different color pen for this so we don't confuse that. So I'm going to have maybe, I'll put it over here actually. It's not really organized, but oh well. So we're going to have S, A, B, C, and D. And currently we can have, so I guess we're going to have S as our starting node. So I guess I didn't put that there, but I guess always assume that S is your starting node. That's kind of, if it's not written there explicitly, just always assume that. You can't go wrong with that assumption. S is your starting node. Okay. So now we first have to process B goes to A. So B has the weight of infinity plus -3. A will remain infinity. We can't update A really. Okay, so that's too bad. So our next edge, we have A goes to B next. A has the weight of infinity because we're looking at A goes to B. So looking at our W array, A has the weight of infinity. Plus 5 is infinity, so B can't update. So, okay, that's a bummer, but is what it is though. And then D goes to B, same argument. D has the weight of infinity plus -2. We can't update B because this is not going to give us a better weight. Okay, so step 4, C goes to A. Same reason as before, we can't update A because C has a weight of infinity plus 2. Infinity still, so A remains the same. Step 5, same issue, because C has infinity for its weight, plus that edge weight from C to D is 4. So D remains infinity still, so we couldn't update anything there either. Step 6, same problem. A has the weight of infinity, so the edge from A to C, first look at A's weight of infinity, looking at our W array, plus the edge weight of 1 is still going to be infinity, so can't update that. And finally, looking at this one, S goes to A. S has the weight of 0, plus 3 will update A that have the value of 3. And then for step 8, S has the weight of S to C, so S has the weight of 0, plus the edge weight from S to C is 5, so C has the weight of 5. And then we're done with our first pass. And now that we updated A and C, now when we do our second pass, we can update all of A and C's neighbors. And if those update, we can update those neighbors. We keep doing this. In this case, we're going to do it 1, 2, 3, 4, 5. So 1, 2, 3, 4. So we're going to do at most 4 steps. Because once again, well, actually, I think you may have to do one more step, actually. I think after v minus 1, you have to do one more step, actually, to verify it, I believe. Because after v minus 1, we can have our best paths in the worst case. We have to do one more step. So the rule is, once you do one pass, nothing updates, you're done. So I believe you do v minus 1, and you do one more step, I believe. I'm trying to remember this. You do one more step to kind of validate that, okay, nothing updated, so we're done. But that's because I chose this order, it's not going to be very optimal, because a better order would have been to sort of have S goes to A first, you pick that edge first, update A, and all of A's neighbors can update also all in one pass. But in the worst case scenario, however, you may not update in that order. You may have to, you made edges will maybe edges will be looked at in this order, let's say, and you only updated A and C only after the first pass. And now using these new weights, we can continue. And I guess the rule is, if after one pass nothing updates, you can stop. Because that means nothing ever will update, because the whole idea of Bellman-Ford is that in a programming problem, we update, and using the updated values, we take those results and try to update newer paths. If nothing updates, though, then we're wasting time, basically. So that's how you want to do assignment question 3. So that's how you want to approach this. You just do this over and over again until finally nothing updates, then you can stop with this problem. So that's that. So hopefully that's kind of cleared up a little bit. So not a very hard algorithm. It's just very tedious, but it's not hard. So, but always make sure you're always consistent with the ordering, or else with the edges of how you're processing them, or else you're really going to make all kinds of mistakes possibly. So be consistent. So just label what order you want to process the edges. And I gave you the order right here, actually. But in general, always make sure you have the orders. That way you don't mess something up. So anyway, any questions on this assignment question or anything on the what I covered so far? Yes, so on the exam, you're going to have an ordering that's going to be something like this, just to make the question a bit longer. So you can't make it easy, I guess, right? We are in CS after all, so you got to make it as hard as possible, and nothing can be simple. So that's the rule, I guess, right? So it'll be something along these lines will be the ordering, just to kind of make it more work, I guess. But you'll have 2 hours to work on the exam, and the actual size of the exam will be about the same as the midterm. It's really just a second midterm, really. So time shouldn't be a factor either way. So I guess that's the good news, I guess, as well. So, any other questions on at least what I've covered so far today with Bellman-Ford and this example right here? That was nice. It's not so bright anymore. Okay, so basically, runtime analysis for this is pretty simple, actually. So basically, this for each loop right here is look at every edge in your graph. So that for each loop will take O of E time. So let's go ahead and just run the runtime here. Now I'm going to go ahead and do one more example with Bellman-Ford. I have about a half hour left, so plenty of time to cover this last example. But this is the runtime for the generic case for Bellman-Ford. So runtime analysis. So basically, the inner loop runs O of E time. Is going to basically just for each edge. So it's, and each relaxed step, the relaxation step is constant, because you just simply look at the array, go to whatever index it's really, so doing this relaxed work is really a constant operation. So the inner loop portion runs all of your time, no problem. And the outer loop, well, as you can already imagine, outer loop runs O of V time. So the runtime overall is going to be O of EV. I guess you could say VE, but I guess EV sounds kind of, it's like a nice name, EV. So that's the runtime for Bellman-Ford. Because you're going to do this for each loop, which will run E times, and then you have to run in the worst case V minus one number of times. So it's, I guess it's VE, but I just chose EV instead. It's easier to remember EV, I guess. So that's the runtime for Bellman-Ford. Now, of course, it could end earlier if no updates happen. So this is actually the worst case scenario where every single pass updates minimal amount of nodes. So you're going to have to do more passes to finally get your shortest path. But you could actually run this faster because you could, so the program can end. So can sort of finish sooner if no update occurs after a pass. So in theory, after v minus one number of steps, it's going to be done because you could do one more step. So after v minus one iterations, on your vth iteration, nothing should update ever again. So that's another sort of focus here. So what if after v minus 1 passes are done, and after the v minus 1th pass, or sorry, on the, what am I talking about? On the vth pass. On the vth pass, an update occurs. So what does that imply? Well, this would imply a negative cycle. So I'll put this here in red. This implies a negative cycle. Is actually on the homework, there's a question like this. And here's sort of my kind of example. So I guess I'm giving the answer away for the homework, which is fine because, you know, for this class, the homework is really just a preparation for the exam anyway. So not too bad to give out the solution, I guess, for this question. But anyway, so basically, the best possible weighted path would have to use up v minus 1 possible edges, which would include every single sort of how shall we say node. So for example, let's look at the following kind of graph right here. Let's say we have the following. Let's say it's the best path we can. This is the shortest weight path actually. Is this. I'm going to go ahead and just maybe add some extra edges in here. Like that. So let's go ahead and highlight the, so these white edges right there are going to be, that's going to be the path, has a shortest weight path from, I guess, U to V. So it's going to be these edges right here are the, this is going to result in the shortest weight path. So the longest path with smallest weight has to be at most v minus 1 edges. So it's going to include every single node is going to be included. Now, if let's say the best weighted path is more than v minus 1 edges, that means we're going to go back in circles, essentially. So going in circles, and we're getting a better path now. So imagine, let's say we take this, let's say we do this, we have this following path, so we choose, let's say we choose this edge, then this is going to be the actual path. Let's say it's not the best path, however. So let's say we try this, then this, and then we circle around. That means we have a negative cycle in our graph. Because there's no way, because we already have every edge, every node's already included in this path. So if we are going to take more edges, we have to go back to a previously visited node in our path, which means that we're going in circles and we have a better pathway, which means we have a negative cycle. So a simple check actually for Bellman-Ford, in fact, is if I do on my vth iteration, if I have an update, then I know for sure a negative cycle is present. So Bellman-Ford actually can be used to detect a negative cycle in your graph. Dijkstra's can't detect that, but Bellman-Ford can detect a negative cycle. All it has to do is runs it v minus 1 times. On the vth iteration, if something updates, then we know negative cycle, because there's no way on the vth step anything can update. Only way that can happen, negative cycle is present, because you're going back to an already existing node in your path. So you're going in circles basically, and you're finding a better path, which is that's only explanation would be that. So that's the idea. So okay, so that's sort of Bellman-Ford. I have one more example left to cover with Bellman-Ford, so I'll probably go over the exam review most likely on Thursday then, because I have to cover one more aspect. So actually, the last sort of thing I'll cover that's new in this class today, and then Thursday we'll do our exam review. So I'll go over the solutions on all the homework and just talk about, have a study guide up as well, and I'll post the assignment 7 stuff once it's due, because I can't really post it, now, because I gave away one answer. So I want you to kind of work on the homework to prepare you for the exam is the idea. But one last thing I want to do for Bellman-Ford is I want to apply this algorithm on a directed acyclic graph. That's our last step. This shouldn't take too long, actually. So Bellman-Ford on a directed acyclic graph, or I guess DAG is the abbreviation for that. So consider the following graph over here. So I have to actually draw this thing, unfortunately, so that's fine. So how many edges, how many do I have here? I think I have, okay, so let's do this. I'm gonna try to do this as fast as I can. I do have about 20 minutes left, so it shouldn't take too long to cover this example. It's kind of an easy example, to be honest. So we'll have, just put this down a little bit. Then we'll have this edge, sorry, this node, sorry. Then we have this node, and we have 2 more. Okay, perfect. Okay. So let's go ahead and I'll put these here. So we're going to have no cycles in this graph, obviously. So we'll kind of see in a second how this actually works, but this is going to be an improved runtime actually if the graph is acyclic. So that's kind of neat with Bellman-Ford algorithm actually, which can't really improve this, I don't think, with Dijkstra's. I don't think you can. So this is kind of a nice scenario for Bellman-Ford. Then we'll have this edge over here. We have this edge over here. Then we have this one. I believe egos. This one also perfect. And what else we have? And I guess we also have this one as well. Oh wait, that's not correct. That's gonna have a cycle. So let's try this actually. Okay. So this has no cycles I can see. So I know it actually has an error because it has had a cycle in that graph. Okay, so I'm gonna have, I guess, I'll have S, A, B, C, D, E, and F. Okay, so since this graph has no cycles, then what's the nice feature we can do? Well, we can topologically sort this graph because there's no cycles. So let me go ahead and just kind of eyeball this topological ordering over here. So we're going to have S will be first, IC and A would be next, then B would, actually, then we have S, and then we have D comes next, so that. Then we have B, then we have E, and then we have F, and then C. So I believe this is a proper topological ordering because, let me see, because we can't go to B before you have been to S and A first. We actually have to go to S, A, and D first before you can even go to B, so that makes sense. And we have to be at B and D to go to E. We have to be at B, E, and F in order to be at C. So yeah, so this is a proper ordering. Okay, so we have this order right here. And this is kind of where we can sort of really in one pass, we can actually do this because there's no cycles in our graph. So because of that, we can make the assumption that, okay, so you first look at S. S has the weight of 0 because S is going to be your starting node. And then A, well, the only neighbor that A could possibly have, well, A right now we have the incoming neighbor S. So we first have to actually take our graph and we have to sort of convert our out neighbors list into an in neighbors list. We have to sort of store every neighbor, every incoming neighbor. So for A, we're going to store S as a incoming neighbor of A. And then for B, we're going to store basically S, A, and D as incoming neighbors. We have to take our adjacency list and a graph potentially, which would be our out neighbors list. We have to convert it into an in neighbors list, which would take O of E time to do, which is not going to be a big problem. So here we can see that, okay, so for A, we only have one incoming neighbor, which is S, has the, oops, I should have put actual weights over here first. Got a little too carried away for a second, my mistake. So let's add the weights in first, actually, then we can continue. My mistake. That would have been a very boring example then. So let's try, this will be, I guess, maybe 2. And then D's will have maybe -1 again. We'll have a 1, we'll have 2. We'll have 1 over here, -3 and 2. Okay, now it's complete. Okay, so look at all of the incoming neighbors of A, which is only S. S has the weight of 0 plus 2. We're going to update this to be 2. And the beautiful part here is that A can never update. So Bellman-Ford algorithm, it may update A more times, but because there's no cycle, there's no other way to get to A except, through S, which is pretty cool. Looking at our next element, so we're going from left to right, so look at A first, now looking at D next. So for D, we look at all of D's incoming neighbors. So D only has one incoming neighbor, which is A to D. So A has the weight of 2 plus the edge weight from A to D is 2. So D is now going to be updated to 2. And also, same thing, since there's no cycles in this graph, there's no way we can ever get back to D in any other path. So that's going to be the best weight. So that's going to be actually set in stone. Now let's look at our next element, which will be B in this array. Looking at B next, so B has 3 incoming neighbors, S, A, and D. Let's look at each one of them. So let's first look at S. So right now we see here that S has a weight of 0 plus 2. We're going to update B to be 2. Now we also have other neighbors of B, other incoming neighbors. So A is the other one. So A has the weight of 2 plus -1 is going to be 1. So we're going to update B to now be 1. And the other incoming neighbor of B is going to be D. D has a weight of 2, and then plus edge weight of 2 to B is 4, so we're not going to update B. So B has the weight of 1, and it will never change. Because since there's no other way to get back, we can't get back to A or S or D in any other way. There's no way we can get a better pathway from S to A, from S to itself, or S to A, or S to D. There's no way. So there's no way we can get a better pathway to B either. So moving along, let's look at E next. So E has 2 incoming neighbors, B and D. So looking at this, so B has the weight of 1 plus the edge weight from B to E is 1, so E is now going to be 2. And looking at D, so D has the weight of 2 plus the edge weight of -1 is going to be just 1 now, so we updated E to a better weight because we first had it from B. Well, actually, either way, it's going to be. I made a mistake here because it was supposed to be either way. I think because B has the weight of 1 plus 1 would be 2. My mistake. And then from D, actually no, I wasn't wrong. Guess I'm getting a little bit loopy into the semester. So um, now from D has the weight of 2 plus the edge weight from DD is -1, which will be a total of 1. So we found a better weight. And same thing, E will never be updated ever again because since there's no other way to get back to E, and also all of E's predecessors, there's no way to get back to them either because there's no cycles in this graph. That means so far S, A, D, B, and E are now fixed. They will never update ever again. Now, our next element we have is going to be F. F only has one incoming neighbor, which is going to be just E. So E has the weight of 1 plus the edge weight -3. It'll be a combination of -2. And that's it. F will never update. So our last element in this list is going to be C. And then for C, well, we have 3 incoming neighbors, B, E, and F. So let's look at B first. So B has the weight of 1 plus the edge weight from B to C, which is 2. We add those up, we're going to have 3. We're going to update, we're going to relax C. Now our next neighbor, which is going to be E, E has the weight of 1 plus the edge weight from E to C is also 1. So the combination is 2. So you find a better weight. We're going to relax C. Our next neighbor is going to be F. F has the weight of -2 plus the edge weight from F to C is 2. So it's going to be actually 0. And that's it. And we're never going to have to do any more passes because since there's no cycles, we know that essentially all the elements, so for example, for C, right here, we only look at just these 3 elements. So for C, we have B, E, and F. And those are the only incoming neighbors, and B, E, and F are never going to be fixed, never going to be modified ever again. So once you modify C, then C can't change because there's no other way to get to C, and there's no other way to get back to B or F. Because an example above, in our earlier example for Bellman-Ford, the problem was, since there was cycles in your graph, there's a chance that we could find a different path that goes back, or not really a cycle, but there's a way to get back to B using a different path. And then so let's go back to our example above, just so I don't go crazy here. So for example, over here, we found a better path to, let me see, so maybe I guess it's kind of hard to decipher all this. But the idea is that we modified A was 6. We found a better path later on because other nodes were updated. And because they're updated, so let's say, for example, we updated B to be a smaller value. And because of that, we updated A from 6 to 2. So the thing is that since we have neighbors S and B go to A, but there's a chance that we could find another path, a better path to B, and then from there we update to A. But in this no cycle version, that can't happen. We can't update E and then, oh wait, I found a better path to D actually, which is going to give me a better weight to B. That can't happen because there's no cycles in your graph. Once we have it fixed, since we have it topologically sorted, we just basically know that there's no other way to get back there. So that's kind of the benefit. So basically, all we have to do is, if there's no cycles, we first have to topologically sort the graph, which we did. And then we're going to basically traverse the nodes in topological order. And then and relax each node using each node's in-neighbor list. And that's it. That's the algorithm. And we see here the runtime for this is going to be O of E. Because for every single node, we look at all the incoming neighbors, so looking at every single edge, basically. So every time I look at a node, all the edges are going to be looked at. So if we look at all the nodes, every edge will be processed. So it's O of E, actually, because the graph has no cycles, because we don't have to constantly do more passes, because we do one pass like over here, and we can stop. Where if it's cycles in your graph, well then there could be other paths that can reweight any node, and because of that, it could reweight all of its neighbors. But here, that can't happen. So it's O of E in runtime, which is kind of nifty. So I guess that's an improvement of Bellman-Ford over Dijkstra's, but that only improves if the graph is acyclic. But then again, it's relatively common actually to have an acyclic graph. So for the most part, it can be actually improved. You can get a better runtime than O of E log V, just using the topological ordering like this. So basically, that was just kind of, another example of a dynamic programming problem with graphs. Now, of course, there are other algorithms for shortest paths as well, which I'm not going to really talk about that right now. Just give an honorary mention to these ones. So we actually have, I believe we have Floyd-Warshall algorithm, which is actually a dynamic programming problem. It's going to be dynamic programming algorithm for all pairs. Shortest path. So, Bellman-Ford and Dijkstra's only work for a single source. Floyd-Warshall will work for all pairs. It's going to find the shortest path between any two nodes in your graph. And it requires us to also use dynamic programming. It's kind of a simple approach, but it's also kind of tedious as well. And it's going to be O of V squared runtime. Actually, no, not V squared. O of V cubed is runtime for this one. We actually have a matrix, and we have to sort of traverse the matrix in a certain way, so we do O of V cubed time. Now, there's actually another algorithm, which is going to be Johnson's algorithm. And it's going to be a greedy approach, but what it does is it's first going to reweight all of the edges because since negative edges are possible, it's going to be using Bellman-Ford's algorithm to actually do this. So it takes Bellman-Ford to find a way to reweight the edges in such a way that's not going to modify the potential shortest paths. So I guess sort of the hint on the assignment, if I were to add some big constant at every single edge in my graph and run Dijkstra's on that, it might not give me the same shortest path, or same shortest, not the weight, but the actual path. It might not be the same path generated by Bellman-Ford anymore. So that's like your hint on that assignment. But with this algorithm, we take this graph and we sort of do some Bellman-Ford on this graph to find the optimal, or find the way to reweight all of the edges in such a way to still preserve the same potential shortest paths as you would get if you used Floyd-Warshall's algorithm. And then you basically just run Dijkstra's algorithm um, for each node. So you pick a different start node each time. And this algorithm is going to take, actually, I kind of forgot, I think it's going to be V E log V, I believe, which can be better. Now, if the graph is dense, however, then it's going to be worse than Floyd-Warshall. If it's a sparse graph, then this is going to be a little bit better, actually. It'll be V squared log V then, if it's a sparse graph, because then E would be a V then. So obviously, I don't have time to cover all these in this class because we are sort of at time. And then on Thursday, I'm going to go over the exam reviews. I'll have a study guide posted. I'll go over a study guide, and I'll go over the assignments we've had this semester because that's going to be a big bulk of the final exam. I'll have the ABED quiz up hopefully soon. It'll be done online. You'll have until Sunday to do it. Just make sure you do the ABED quiz, do your best on it. I'll give extra credit points for the final exam for that. So that's going to be it for today. And then Thursday, we'll continue with the exam reviews. So for right now, I guess, take care, stay safe. Thanks for watching. Have an awesome day. And I will see you on Thursday.